Hello, my name is Masaki Miki. I'm an assistant professor at the University of Tokyo. Today, I'm going to present about general methodology to solve tension compression mixed from finding of shells. First, I would like to mention that at the moment I was preparing an abstract and full paper, I had one paper that was recently accepted for publication. Therefore, I am now be able to fully elaborate on the technical detail of the method. Those details are not included in the full paper. If you are interested, please check out these two papers online. Here are two images showing pure compression domes designed by the famous structure engineer Edward Troja. As you can see, the shapes in pure compression are always dome-like. At the same time, there are fake shells designed by star architects. Although engineers may say these are fakes, I believe they are beautiful and elegant. As you can see, they have nice overhanging free edges stretching out towards the sky. In addition, we already have these beautiful thin surfaces made of reinforced concrete. They are considered nearly tension compression mixed type shells. Therefore, if we find a way to computationally find the shapes of tension compression mixed shells, we can expand the possible forms that the shells can take. This consideration strongly suggests that computationally finding tension compression mixed forms is an important topic to discuss. In the membrane shell theory, we use area-state functions to describe the in-plane stress state. An area-state function is a surface whose curvature is interpreted as the stress in a shell. Therefore, we can select a pure compression stress state by selecting a stress function with a positive Gaussian curvature and tension compression mixed stress state using a stress function with a negative Gaussian curvature. By selecting a stress function with a negative Gaussian curvature, we can expect to find forms of tension compression mixed shells. I started my research with this idea. However, at first, I could not find any existing studies on this, which is strange because many people are aware of the concept of area-state functions and know that negative Gaussian curvature is a tension compression mixed stress state. Eventually, I learned that this is a well-known problem, which is known to be notoriously difficult to solve. The vertical equilibrium of a shell can be represented using the stress function denoted by phi. This is the second-order partial differential equation with constant coefficients. This equation is used to find the forms of a membrane shell. From old books, I learned of different types of second-order partial differential equations. For instance, pure compression is elliptical, which is easy to solve. Laplace equation is a well-known example of this type of equation. By contrast, the tension compression mixed type is hyperbolic, which is known to be notoriously difficult to solve. A well-known example of this type is the wave equation. As it describes wave propagation through time, it is usually solved by giving the initial values of the wave at an initial time and performing incremental numerical integration by updating the wave state with sufficiently small time steps. However, to find the shell form, we must deal with a boundary value problem rather than the initial value problem. If the boundary values of the shell are given as in a membrane problem, then the hyperbolic problem is notoriously difficult to solve. Here is a simple wave equation as an example of a simple hyperbolic equation. It represents one-dimensional wave propagation along time. The waves run either from left to right or right to left. Thus, in the two-dimensional time-space domain, the waves run along the diagonal lines crossing the x-axis at 45 degrees. These diagonal lines are called characteristic lines. In shell form finding, the characteristic lines in the problem are known to be the asymptotic lines of the stress function. This slide shows the proof. As such, in this specific problem, the asymptotic lines of the stress function, which are the characteristic lines of the problem, are exactly the directions depicted by the red lines. In a hyperbolic boundary value problem, the boundary values must not contradict the waves running along the characteristic lines. For instance, the boundary conditions shown on the top left and top right are compatible with the problem, whereas the one shown on the bottom left is incompatible. When the boundary conditions are not compatible with the problem, then the problem has no solution. In engineering, we are usually asked to solve only problems that have solutions. We normally never wonder whether there are no solutions. However, when solving tension compression mixture form finding, we must remember that there is a high chance that no solutions exist. Consequently, when solving a tension compression mixed form finding problem, we must identify boundary conditions compatible with the problem first. However, my search found no existing literature that provides an explanation of how to handle this. Now let's talk about how to solve the problem. We see a reciprocal structure in the equilibrium equation. Therefore, if you pin stress function and find the shell, you can perform shell form finding. Conversely, if you pin a shell and find the stress function, you can perform stress function form finding. These are both second-order partial differential equations with constant coefficients, which means there is a high chance of there being no solution if they are negative Gaussian curvature zones. Now, we consider unpinning both the stress function and shell and consider both of them unknown variables. In this case, as we now have two unknowns and one condition, the problem is under constraint in general and is unlikely to become over-constrained. Here is what's going on. If the problem is a pure compression one, then after pinning the stress function, you can expect to find an intersection with the solution space and unique shell as a form-finding result. Conversely, for tension compression mixed cases, after pinning the stress function, it is highly likely that you will find no intersection with the solution space. However, as the solution space is large, if you started with initial guesses of both stress function and shell and try to approach the solution space, then you can obtain a nice pair of stress function and shell. This time, by pinning the obtained stress function, you can find an intersection with the solution space. Therefore, the shell form finding problem provides a solution by construction, even when there are negative Gaussian curvature zones in the stress function. By stitching together all the elements mentioned by far, a nonlinear least squares problem that takes both the stress function and shell as unknown variables is finally revealed. This type of problem is called a bilinear tensor least squares, or BTLS problem. A BTLS problem can be divided into primal and dual LS problems. The solution methods for BTLS problems are well studied and established. We reference this paper overviewing and comparing three methods. However, the problem is usually found in data science and rarely applied to partial differential equations. As far as I tested, the first two methods, namely the simple alternating approach and Gauss-Newton, did not work well with our problem in my test. Only the third method, called the variable projection method, worked well with our problem. The alternating approach is a simple strategy that alternately solves the primal and dual LS problems. Although you can quickly obtain a rough solution using this approach, the method does not converge in an accurate sense, as solving one condition breaks the other. Likewise, in the variable projection method, we alternately solve the primal and dual LS problems. However, when solving the primal LS problem, we insert the dual LS problem as a constraint condition, so that solving the former does not break the latter. Although this method is complicated and the computational costs are high, it always converges, and the computation is very stable. This short animation demonstrates how the method works. The red one is a shell, and the blue one is a stress function. When the user modifies a shell, it triggers a change in the stress function, which invokes further change in the shell. This feedback loop finally settles, which is the convergence of the optimization method. In conclusion, tension compression mixture form finding is difficult to solve as the problem is likely to have no solution. Solving a BTLS problem by regarding both the stress function and shell as unknowns allows the problem itself to be defined until it has a solution. We recommend the variable projection method to solve the BTLS problem. Thank you for your time and attention. Now, I would like to welcome any questions that you may have. Thank you.